let me begin, just to be very clear, to explain what I mean by new trends. Okay? So, first of all, quantum probability. Quantum probability was born, roughly speaking, 30, 35 years ago, and we were thinking for many decades that quantum probability is a generalization of classical probability. A generalization is a rather natural direction that is, instead of assuming that random variable commute, we assume that random variable do not commute. So 30 years after quantum probability, this idea was imported in other fields of mathematics, in particular geometry, and then became a trend to non-commutativize everything. Okay? What is the new trend? The new trend is this. Quantum probability is not a generalization of classical. It's a deeper level. This means that if you take an absolutely classical random variable, you must arrive to non-commutativity. So I emphasize, the point of view is completely different. Not to put non-commutativity by hands, but to deduce non-commutativity from commutativity. Okay? You will see what I mean. So, this is the fact that classical random variables have a kind of microscopic structure which is intrinsically not commutative. Why now this is a implication in quantum mechanics? Well, in quantum mechanics, you know very well that quantum mechanics has been, the formalism of quantum mechanics has been considered very mysterious from the beginning, even by the founding fathers. It's very famous, this statement by Heisenberg, that the quantum formalism is very far from intuition. There is a famous statement by Nelson that the first quantization is a mystery, while second quantization is a functor. And there are very well-known apparent mysteries of quantum mechanics concerning with the duality wave-particle, and again, why non-commutativity arises. Okay? So, the implication of what I said for quantum mechanics is this, that first quantization is just very old, 150 years old theory of orthogonal polynomial in finitely many random variables. And second quantization is the theory of orthogonal polynomial in infinitely many random variables. You will see here some very subtle and delicate problems arise when you go to infinite dimensions. I hope I have the time, but I have not. So pay attention. I say restricted to Gauss-Poisson class, here only to Gauss, because unfortunately in multi-dimension there is not yet the same equivalence relation that you have in one dimension. That we know that in one dimension Gauss and Poisson belong to the same class. In multi-dimension there are some subtle problem related to the notion of multidimensional Poisson process and of equivalence relation. Okay? So the duality wave-particle, so discrete continuum, is again very natural consequence of orthogonal polynomial. Every, even absolutely continuous random variable is canonically associated to a discrete random variable. At least one. And when we go outside to the Gauss-Poisson class, that completely covers the standard quantum mechanics and quantum field theory, we will enter into what I call the program of nonlinear quantization. Okay. The beginning of all this was in a paper long ago by Lou Volovich and myself, in which we, roughly speaking, summed up some results concerning quantum electrodynamics in the stochastic limit, and we introduced the first axiomatization of what now is called the interacting Fock space. Interacting Fock space was born from quantum electrodynamics, and it is now, as you will see, about a few years later, it was recognized, completely surprising, that this new notion of interacting Fock space was essentially a reformulation of the theory of orthogonal polynomial in one variable. And this came a few years later in a joint paper with Bozeico, in which we proved this identification that I will try to, of course I have no time to give the details, but I will try to give you the main ideas of this identification, okay? So in order to give this idea, let us start with the classical context, absolutely classical random variable, real valued, with all moments. When I speak random variable, I always will assume with all moments. So if I put coordinates on the real line, I will, since I am assuming all moments, I obtain a state on the polynomial, the algebra of polynomial functions, complex valued on the real line. So these are complex polynomials. Okay? And the probability measure will define a state on this algebra by the integral, and the scalar product, in fact, pre-scalar product, because there may be a lot of zero norm vectors, is given by the standard formula where mu is defined above. And now, not all scalar products are on the polynomial algebra are induced by measures with this formula. And it's interesting that those who are induced by probability measures are characterized by the self-adjointness of what in quantum mechanics is called position operator. Okay. And now we orthogonalize monomials, and we get a monic orthogonal polynomial. And 150 years ago, Jacobi proved the famous three-diagonal relation for monic orthogonal polynomials, in which you recognize there appear two sequences, omega n, which is called the principal Jacobi sequence, and alpha n, which is called the secondary Jacobi sequence. Now, let us look at the Jacobi sequence. We don't do anything, no mathematics, only reinterpretation. Take the Jacobi relation and interpret it in operator language. Instead of x, you have multiplication by x. And instead of the operator, of course, since this is orthogonal basis, not orthonormal, monic, so I can define an operator which to phi n associate phi n plus 1, n plus 1. Another operator which to phi n associate alpha n phi n. And this I call A0. And another operator which to phi n associates omega n phi n minus 1. And I call A minus. Okay? Now, since this is an orthogonal basis, oh my God. Oh. Since this is an orthogonal basis, this identity, the Jacobi identity, becomes an operator identity. So the multiplication operator is obtained as a sum of three operators. Now remember, multiplication operator is identified with the standard random variable, the classical random variable x. And so this decomposition is what we call the quantum decomposition of the classical random variable. And this is what I meant at the beginning of my talk when I say that there is a microscopic structure in every classical random variable with all moments. Okay? This microscopic structure is given by the three operators, which we call the cap operators: creation, annihilation, and preservation. So you see, this Jacobi theory of orthogonal polynomial is 150 years old, and people have looked at it from the point of view of analysis. And as I said, we are now looking at it from a new point of view. Okay? And let us see some implication of the new point of view. Up to now, we have not proved anything. We have just looked at a certain object and interpreted this in a different way. But there are some non-trivial consequences. Okay. Remember the quantum decomposition. And remember the definition of the operator A daga and A minus. A daga is the shift, the right shift. A minus is the weighted left shift, weighted by the principal Jacobi sequence. What is the fact that A daga increases the gradation by 1 and A minus decreases by 1? Is that both A minus A plus and A plus A minus leave the gradation invariant. But since the gradation is one-dimensional, it must be a multiple. And you see, this A minus A daga is omega n plus 1, and A plus A minus is omega n. So we deduce the commutation relations. You just subtract this from this, and we obtain this. And you obtain the commutation relation. So, summing up, every classical random variable with all moments is canonically associated to some commutation relations. Let us rewrite the commutation relation in operator language. We introduce the number operator, lambda, defined as usual, and therefore the commutation relation that we wrote before become in operator language A minus A daga is equal to this is a difference operator. You will see it will play an interesting role. But what is the difference with the standard commutation relation? That these are operator valued. In fact, these are functions of the number. I anticipate that that was exactly the definition that we gave in the paper with Lou and Volovich of interacting Fock space. That is how we made the bridge and the identifications of the two, but we will come to this in a moment, I hope. Okay, so we have operator commutation relation. Notice that the commutation relation only depends on the principal Jacobi sequence. For the moment, no role for the secondary Jacobi sequence. So we have an equivalence relation between classical random variables, and we say that two classical random variables are equivalent if and only if they have the same Jacobi sequence, and therefore they have the same commutation relations. So it is very important that the Jacobi theorem is a converse. Jacobi says that given a probability measures with all moment, you get two sequences, omega n and alpha n. And there is a famous lemma which is called the Favart lemma, which is the converse, which says given two sequences, then I get a probability measure. Are the sequences arbitrary? Alpha n is arbitrary. Omega n is arbitrary only to one condition that we will call the Favart condition. And you will see in a moment this Favart condition is a very nice interpretation in quantum mechanics. So this condition is that if some omega k is 0, then all omega n are 0 from that k on. So the sequence has only this constraint. It means this is arbitrary. This difference is arbitrary. We are not requiring the sequence to be monotonic or things like that, okay? In the paper that I mentioned at the beginning with the Lu and Volovich, we defined the simplest possible interacting Fock space, the most elementary, the one mode, corresponding to quantum mechanical system with 1 degree of freedom. And we defined with the 3 axioms. The first is the existence of the gradation. The second is that the norm is defined by a certain element which is greater or equal than 0. And the third is, this is the strongest condition. It seems innocent, but as you will see, is very rigid. That the creator is an adjoint. Because you see, this is a one-dimensional gradation. And the norm, to give the norm of the single vectors of the gradation is equivalent to give the scalar product. So there must be a compatibility condition between the scalar product to have the existence of the adjoint. And the theorem, in fact, is this, that the compatibility condition which guarantees the existence of the annihilation operator is precisely the Favart condition. And this gives the bridge between interacting Fock spaces and orthogonal polynomials in one variable. Okay? So in this sense, we have an, you see, in this sense we have a very nice picture. The orthogonal polynomial in the classical language of analysis and probability will correspond to what in physics are called the n-particle vectors. So there is, however, something missing. Why? Because in orthogonal polynomial, when we defined the interacting Fock space, we didn't think of orthogonal polynomial. And we were very much influenced by standard quantum mechanics, in which you only speak of A and A daga, because you consider the number as a derived concept. A derived because the number is A daga times A. So it's not a kind of a primitive concept. But in the orthogonal polynomial, the preservation operator is an independent nature. And this independent nature was understood about 16 years after, and only through a very, very tiresome analysis of the multidimensional case, which is really much more difficult, okay? But we will come back, I hope, on this point. Now, let us now, before going to multidimension, go to some very interesting remark. So, we have, remember, forget for the moment A0. There is an additional part of the Favart lemma which says the following, that those measures for which the preservation operator is identically equal to 0 are exactly the symmetric measures. So those who are symmetric by reflection, multiplication by -1. Of the real line, okay? So to restrict to A plus and A minus is equivalent to restrict to the symmetric probability measures. For example, standard Gaussian, okay? So, and remember the formula of the orthogonal polynomial commutation relations. So this is the formula, and in standard quantum mechanics, this is a constant times the identity. But in general probabilistic quantum mechanics, you have an operator which is a function of the number operator. So, we can ask the following question. Since we have this commutation relation, remember, the probabilistic commutation relations are this. But we don't know if this gives a closed Lie algebra. Because, of course, if I put a central element, the identity plays the role in Lie algebra of the central element. So if I put a central element, I have just a trivial central extension. And it is a closed Lie algebra. But this is an operator. So it's not clear a priori that if I take the commutator of this with A plus or A daga, I still obtain something in the Lie algebra. And so we can ask, under which condition the algebra generated by A minus A plus is finite dimensional? Of course, this algebra must contain this operator. And so you understand that the difference operator will play a role. Okay? And so this is the question. And the theorem is, if you take a single real-valued random variable, then you have a necessary condition. Remember, delta is the finite difference operator. So the necessary condition is that the principal Jacobi sequence satisfies a difference equation starting from a certain point on of the natural numbers. So initial condition is not at 0, but at k plus 1, let us say. It is interesting that this sufficient condition is not necessary. It is necessary if and only if this n, the n which is the degree of the difference equation, is 0, 1, or 2. Starting from 3, we get an infinite dimensional Lie algebra. It's a very interesting Lie algebra. So, let us see what happens. This makes an interesting bridge with all the Kolmogorov complexity theory of algorithms. You see, Kolmogorov proposed a very, he was trying to define randomness as a kind of infinite complexity. And so he proposed a way to measure complexity of sequences. But since we are now classifying probability measures in terms of sequences, it's very nature to introduce a complexity notion for the sequences in the complexity in the Kolmogorov sense, and to look of the sequences which characterize the probability measures. So we introduce the complexity index given by a pair of natural numbers, and remember, this is n means that the functions, the principal Jacobi sequence, satisfies a difference equation of order n. And k means it will satisfy this difference equation starting from k plus 1 on. Okay, now this is a complexity index. Okay, I have short time. I want to just give you some interesting examples. Okay, let us consider the simplest probability measures. The one which have 0 so they satisfy a difference equation of order 1. Remember, the degree is n plus 1. So 0 will correspond to 1 in the degree of the difference equation. So it means that omega is constant, if the difference equation. Omega is constant, but there are two possibilities. The constant is 0, the constant is not 0. And then it must be strictly greater than 0 because it is a Jacobi sequence, okay? The first case is rather simple. The first class just are the delta measures with omega 0 equal to 0. The second class is rather interesting because if you take the 0, 0 complexity index, you find a familiar object in quantum probability, which is the semicircle law. Semicircle law corresponds to the simplest possible probability measure. Let us go to the next step, 0, 1. So still you satisfy 0, you see, why 0, 0? Because the semicircle law has a constant omega. Omega n is constant, starting from 0. In the arc sign, omega n is constant starting from 1. And therefore, you understand that the 0K laws are natural generalizations both of semicircle and arc sign. It is very interesting that the 0-2 laws have recently appeared in some paper by Conno on quantum random walks. Starting from 3 on, we don't know anything about the structures of 0K measures for K greater or equal than 2. For example, F-dia density. They are really the simplest possible classes of probability measures. But we know very, 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 very little about them. And of course, we know from general theory, I will not discuss it here, but we know that these measures correspond to the Gaussian for some notion of independence. Okay? So, which is the notion of independence? We know that for semicircle is free independence. For arc sign is monotone independence. And already for K equal 2, we don't know what kind of independence concretely it is associated to this measure. More interesting is the class 1K, because 1K means that you have a second order difference equation. Second order difference equation, the general solution means that omega n is Bn plus C. And of course, it must be positive, so there are some constraints that you can easily compute. These constraints are very interesting when you classify finitely supported measures, but I will not discuss this. What is interesting is that if you take 1, 0, so the difference equation starts to be valid from 0, you get both Gauss and Poisson. You get both Gauss and Poisson. And the Lie algebra is exactly the Heisenberg algebra. So you see, when I said at the beginning, quantum mechanics is a corollary of the theory of orthogonal polynomial, because the Heisenberg algebra corresponds to the 1, 0, so it's rather simple Heisenberg algebra. But don't forget, they are the only finite dimensional one. So there is only one more finite dimensional Lie algebra. They correspond to the class 2K. What is the class 2K? They satisfy a third order difference equation, so the solution, general solution, depends on 3 constants, okay? And these 3 constants, what give? Well, to make it short, I see the time is very short, you get exactly the non-standard Meissner class. You know that there exist exactly 5 Meissner classes. And the first 2 are Gauss and Poisson. And they are covered by the index 1, 0. And the index 2, 0 covers the remaining 3 Meissner laws. Okay? what is the Lie algebra corresponding to the Meissner law? In the case 1, 0, we have Heisenberg algebra. In the case 2, 0, we have SL2R. The algebra of Meissner law, this was in another paper with Volovich and Liu, where we introduced it, quadratic quantization. Quadratic quantization corresponds exactly to Meissner laws, to non-standard Meissner laws, okay? And so, in fact, it's a central extension of SL2R because it's 4-dimensional, okay? There are classes of Beziers which do not satisfy the necessary condition. So they don't satisfy a difference equation. It means the sequence omega n is not of polynomial type. And this is the Q deformed, and there are many very interesting Q deformation. The standard Q deformation corresponds to the choice omega n to be exactly like this. But this forces the parameter to be real, and in this case, positive. I mean, you have also fermions, but I don't want to discuss it. Okay. But there are other Q deformations. For example, a very interesting, this has to do with the famous bosonization theorem by Partasarati and Hudson, and it corresponds to a different Q deformation. The Q deformation parameter is, the Q commutation relation is here not constant, but Q to the power lambda, okay? And there is still another. There are many other examples I have no time to go into. So let us now recall that we have proved the following theorem. There exists exactly one equivalence class such that the commutation relations give the Heisenberg algebra, and this equivalence class is exactly the Gauss-Poisson class. Okay. So if standard quantum mechanics corresponds to Gauss-Poisson class, which kind of quantum mechanics will correspond to the other classes of probability measures? This is a very natural question. And let me try to give a few words about this. I will try to, sorry. Okay, so I will just outline how you can build up a quantum mechanics associated to arbitrary probability measures. So you can define the Schrödinger equation, and as usual, and we begin to work at Lie algebra level. And we introduce the free Hamiltonian associated to a random variable x. Remember, x is a classical random variable. And we have the canonical commutation relation associated to the random variable x. Now, we define the free Hamiltonian as usual, just a constant positive times a daga a. Then we define the Schrödinger equation, and we see the solution is very similar to the usual harmonic oscillator, only that this is a non-commutative harmonic oscillator, because, you see, here, A minus doesn't commute with the lambda. And of course, A plus doesn't commute. So we have a formula which is very similar, but nevertheless non-trivial. And then we know by general theory of Lie algebra that the evolution, automorphic evolution on the Lie algebra level is extended to the enveloping algebra, which is the polynomial algebra. Is a non-commutative algebra whose subalgebra is the standard classical polynomial algebra. I just want to say why this exercise can be interesting. This exercise can be interesting because the orthogonal polynomial commutation relation can be bosonized. So you can read this very simple evolution when in the orthogonal polynomial space in the usual boson space. And there will look terribly complicated. So this is like what happens in integrable Hamiltonian systems when you go to action angle variables. When you go to action angle variable, all integrable systems are harmonic oscillators. And here we have a method to produce infinitely many examples of quantum integrable system. Okay, the multidimensional will be in the next conference. Thank you very much.
Questions, please.
Can I ask a question? You present us a scheme to reconstruct quantum mechanics from classical probability theory. I would like to ask you, where is H bar?
H bar is this famous constant, which in mathematics is an arbitrary constant. But of course, physics.
I don't yet see it in the formula.
Because when you solve the difference equation of when you have the difference equation, the solution will be Bn plus C. This constant is what gives you. We have seen that the quantum mechanics is characterized by the fact that the omega principal Jacobi sequence satisfies a second order difference equation. The constant that appears in the general solution is exactly Planck constant. Of course, in the physics language, but this is mathematics. For mathematicians, all constants strictly positive are equivalent. In physics, fortunately, it's not so.
Okay, ask some more questions. Let us thank the speaker again.
Thank you.